I want to start the day with a little bit of review from yesterday. And normally in organic chemistry classes, professors like to use ethanol as an example. I just want to mix things up a bit. So instead of ethanol, I'm going to make a stretch and use diethyl ether. And hey, even professors make mistakes. Let's fix that. We're in a hurry. Okay, so how is this going to look in an NMR spectrometer? The first thing I want to focus on is identifying the different types of protons that are present. So the methyl group is clearly different than the methylene group. This methylene group over here, though, is the same as the methylene group on the other side due to the symmetry of the molecule. So we have, and then the same is true for the methyl group on this side. So we actually have two different types of protons here. And we'll stay with the same thing, HA and HB. These protons would be HB. And I'm just using A and B as descriptors to distinguish between the two. You could probably use something else, H1, H2, or something like that if you wanted. All right, so that addresses the number of signals. We're going to get two signals here. And now let's talk about where they're going to show up in a relative sense. Because of the electron withdrawing capabilities of oxygen, HB resonances are going to be higher frequency than HA. So I'll just say HB greater than HA, and this is with respect to the chemical shift, the ppm value, which is delta. So we expect the methyl group to show up first, if you will, going from right to left in the NMR spectrum. How about integration? We have six different protons that are methyl groups. So HA equals 6 and HB equals 4. So the ratio is going to be 6 to 4. And that's because of the fact that we have 6 to 4. I'm just counting all of the methyl group protons that are the same, and there's 6 of them, and then I'm comparing them to the methylene protons, and there's 4 of them. So that's what we expect for the integral value. And then the last thing is the splitting. Methyl group here feels the influence of the methylene group right here. These two methylene hydrogens, I'll explicitly draw them out just for this one. And I better erase some hydrogens, otherwise I'll have way too many bonds to carbon. So I'm just drawing out this one methylene group. We're 3 bonds away, so HB definitely affects HA. Coupling will not occur through the oxygen, and HB over here is way too far to influence HA over here on the right side. So HB on the left will not influence HB protons on the right, but they'll definitely influence those protons that are right next door. All right, so back to the methyl group and how it's split. It's going to be split by 2 protons, and remember the n+1 rule? n+1 means that this methyl group will show up as a triplet. A triplet not because there's 3 protons here, but there's one more. A triplet because there's 2 protons nearby. n+1 relates to the 2 protons that are actually doing the splitting. So we'll go CH3. CH3 groups will be a triplet. And following along then, CH2 groups are going to feel the influence of the methyl group. There's 3 protons there, so N plus 1, that makes it a quartet. All right, this should be your thought process, pretty much in the order that I have given it, for when you are faced with trying to figure out what the NMR spectrum of a compound would look like. Think about the types of signals that are going to be present, roughly where their chemical shifts are going to be relative to one another, the ratio as determined by the integral, and then the splitting. With those 4 items, we have everything we need to do to predict the NMR spectrum of ethyl ether. And I've drawn the structure out here on the left in its detail with all the hydrogens, basically all the atoms. And then the shorthand version that I know everyone is familiar with. Looking at the shorthand version, this little figure kind of looks like a person with a shoulder shrug. I hope that's not the case for us. You guys are following all this pretty clearly, I'm sure. Okay, NMR, triplet, right? Triplet, quartet, and you'll see like little T's and Q's in NMR data. That just describes the splitting of the peaks, the coupling to other protons. And we know this is going to have a lower frequency. I'll just go low, and frequency is that little nu. And then these are going to be higher frequency. Little nu there. Okay, so let's just draw it out. First is our triplet, 1 to 2 to 1. And then our quartet, 1, 3, 3, 1. And appearance in terms of the peak height, remember that relates to the probability. I haven't explained 1, 2, 1 yet, and I will in a moment. But you remember the quartet from how the 1,2-dichloroethane was split by the adjacent methyl group. So that's what you have here. So these 2 hydrogens on the methylene are that peak. The methyl is that peak. And if we had TMS down here, it would be like a little peak there. And that's it for the NMR spectrum, because this methylene is the same, and this methyl group is also the same as the one on the other side of the molecule. We have that nice plane of symmetry. So the left half is identical to the right half. If we were to integrate these peaks, we would have the ratio of 4 to 6, which is a ratio of 2 to 3. So whatever the integral is, and I'm going to stop drawing those lines over the peaks. That technology is so antiquated. The textbook has it, but it's time to bring you guys into the modern world. So far, that's the one criticism I have with the textbook. They can be doing a little bit better in showing NMR spectra the way they are these days, in this century as it is. One common way that modern instruments would report data is with the values underneath the peaks. So wherever the brown part of the pen touches the ppm scale, which is your signal, that's where you start your integration, and then on the other side, that's where you end. And then in between, the values that are there are going to correspond to the area underneath the peaks. And the thing is, it's one peak, but it's just split 4 times by the coupling. But we could set that area to 100, and that means the area underneath the triplet is going to be 150, because that's the ratio as required by the molecule. All right, so one last time. On the old instruments, you would have this line, and it would go up and it would stop after it went up by a certain amount. And then this one would be sorry, Mr. Guy, I'm going to be in your way. It goes up like 1.5 times. So if this value were like 15 centimeters, then 15 times 1.5, man, I made that hard on myself. Hit pause. Okay, 22.5 centimeters, 22.5, because that's 1.5 times the intensity of the quartet, and it has to be. 4 to 6 is equal to 2 to 3 is equal to 15 to 22.5, or 100 to 150. So maybe this is a limitation of NMR in the sense that if you have a peak with symmetry, if you have a compound with symmetry, you're not going to like know right away how many protons, but you will know the ratio, which is still very, very useful information. Okay, so next slide, I'm going to talk about N+1 with respect to ethyl ether. And I'm going to erase some things before I do that. So the appearance of the peaks regarding the splitting always has a shape that is predictable by the probability. Remember the arrows from yesterday? When you had 3 arrows and you wanted one of those arrows to be up, there were 3 possible places for that arrow to be. This is straight probability. So if you ever do any high level classes in statistics and mathematics, and all you genetics folks, I know you will. And I wish you all the best with that. But it's Pascal's triangle. That's how you can calculate how these peaks should look like based on the number of protons that are splitting them. So if you have one peak with nothing coupling to it, and we had a whole bunch of examples of that. Well, hey, TMS is a great one. Si, remember you have these 4 methyl groups that are all the same. So there's nothing splitting tetramethylsilane. TMS contains 12 protons, but they're all the same, so it shows up as one peak. Let me just quickly put up Pascal's triangle and then show you how it relates to these 2 resonances that we have for ethyl ether. On one of the rows of Pascal's triangle, you'll see 1, 2, 1, the numbers. And then the row below it, 1, 3, 3, 1. That describes the relative heights of the peaks that are split due to the coupling to the adjacent peaks. And what I'd like to do now is just 10 seconds or so show you Pascal's triangle and how it's assembled. Even university instructors will use Wikipedia, or at least I do from time to time. This is an animation from the wiki page that shows you how Pascal's triangle is constructed. And as you see, the values for the numbers represent the sum of the 2 numbers that are directly above it. That's why the numbers kind of stagger as you go down the row of the triangle in Pascal's triangle. And let's talk about how this relates to NMR. This is the whole point of putting this up. If you have one peak, one NMR resonance, like TMS, because it's not split by anything, then you just have one peak. And that is just intensity of, when you integrate that peak, it'll be whatever value you want it to be. If that NMR resonance is split by a hydrogen and only one hydrogen that's adjacent to it, the 3 bonds away, then you'll have a doublet. And the intensities of the 2 peaks in the doublet will be 1 to 1. If it's a case where, like in our methyl group for ethyl ether, where the methyl group is being split by 2 other peaks that are next door, then it's a 1 to 1 relationship to those peak heights. And then the quartet is 4 peaks, And we've had two examples of, and the quartet is common. I'll say the quartet is common because it represents the splitting by a methyl group. So the 1-3-3-1 quartet comes from this relationship in Pascal's triangle, which then relates back to the arrows and the different ways I could assemble the arrows. And so on for 5 peaks, 6 peaks, etc. We'll have one example. In fact, let's do that next. We'll have one example where an NMR resonance is split 7 times due to proton-proton coupling. So let's do that next. Here we have 2-bromopropane. And very quickly, let's just talk about the different types of protons. We have the 2 methyl groups, and they're equivalent. So we can call those HA. And then we have this one proton that's bound to the carbon number 2, that's HB. HA is going to be split into a doublet because this HB is 3 bonds away. 3 bonds or less is the kind of coupling you have to concern yourself with. And so far, everything we've talked about has been 3-bond coupling. So HA is going to be split into a doublet. And let's just draw that out. When we know HA is going to be the lower frequency, the lower ppm value, because it's farther removed away from the electron withdrawing effects of the bromine. Bromine being electronegative, making HB relatively more de-shielded compared to HA. Now, how is HB going to be split? It is going to be split by 6 equivalent protons. They are the same because of the plane of symmetry, so HB feels the effect of all 6 of them equally. And if you look at Pascal's triangle, that would be a septet. And the splitting ratio of a resonance split 7 times is going to be 1 to 6 to 15 to 20, 15, 6, 1. The wiki animation didn't go that high. But in your textbook you can see that example. So at a higher frequency, now here this tests my ability to draw it. And in reality it's going to look probably, you see what I'm doing? I'm going 15 and now 1, 6, 15, 20, 15, something like that. But the whole idea, I'm going to clean this up a little bit. Okay, I cleaned up my figure a little bit. The point I'm trying to make here by drawing this out is that the peaks on the end are relatively small, and they should only be an intensity of 1, and I messed up this peak here. I'm going to make him smaller. The next peak over should be 6 times the height, and then 15 times the first one, and then 20 times, and then 6, and then back to 1. 7 peaks that look like this intensity. And it comes from the n+1 rule. So n+1 tells you that you're going to have 7 different splittings for your resonance. And that means that the 6 protons, so what you do for n+1 is you say, okay, I got 6 of these HAs, n+1. That means this resonance will be split 7 times. And then if you want to think about the appearance of how they're split, then you use Pascal's triangle to show you what the intensities are for those 7 peaks within that split resonance. And then for the doublet that corresponds to the methyl groups, you will have just 2 peaks, because it's only split by HA. All 6 of the HAs are only split by 1 HB. Okay, that's the splitting. And here's where I think a lot of students get lost. The integral. What about the integral? The integral is going to be such that if I made the integral for the septet 100, then this integral would be 600 because I have 6 resonances, 6 of the HAs to 1 of the HB. Okay, I think the thing to do now is just to kind of go through and look at some NMR spectra, and I'll just describe to you why they look the way they do. And it'll be reinforcing all 4 of these things with an eye, I think, toward the n+1 and the splitting. And before I leave this slide, I just want to revisit J. J is the coupling constant. So remember, the splitting between your peaks for like the doublet is going to be the same as the splitting between each individual peak of the septet. So I've drawn this not to scale, as it were, not to scale, because the distance between every single one of these peaks along the septet has to be the same distance between the doublet. And that's because of the coupling between HB and HA. The splitting is the same. Before we go, though, I wanted to show you what these spectra actually look like. So I found these NMR spectra from my favorite Japanese website. And this is, well, you should be able to tell me what this is, right? This is diethyl ether. It's probably not 100% clear. In fact, I guarantee you're probably having difficulty seeing that this is a triplet at around ppm, like 1.25. And then our quartet for diethyl ether shows up at 3.5 ppm. So I already showed you exactly how these resonances look, but I just wanted to show you the real life resonances with regard to the ppm scale, because we'll be talking about ppm in quite some detail. So this is diethyl ether, and again, if we were to blow up this region, we would see that nice little triplet with the 1-2-1 pattern. And then the pattern of peaks for the resonance corresponding to the 2 methylene protons that are just next door to the oxygen, that's that quartet with the 1-3-3-1 pattern. Okay, so let's move on to the other compound. This is the NMR spectrum for 2-bromopropane. Our methyl groups are showing up at around 1.25 or so. And then that septet is about 3.75 parts per million. And this is the real life kind of appearance of the peaks. And you can see that this septet overall intensity is much lower than the intensity of the doublet. And that's best explained by the fact that the total signal underneath all 7 of these peaks has to be 1/6 of the total intensity underneath these 2 peaks. So it's very common to see peaks that are split a whole bunch of times and correspond to just, let's say, 1 proton as opposed to 6, be small in terms of their vertical height compared to the other peaks. A methyl group, it sticks out like a sore thumb, as we say, because number one, its location, and methyl groups on the end, by definition, they can only kind of be bonded to one other thing. Be on the lookout for peaks around this 1 to 2 part per million range that may be doublets or triplets and integrate to values that correspond to 3 protons. That's a telltale sign of a methyl group. Later on today, I'll show you some examples of some methyl groups that are at a higher frequency and are singlets. And they're singlets because they correspond to methyl ethers. And by now, I hope it's clear to you why they would be at high frequency and also why they would be singlets. Okay, I think it's time for a break. But before we go, I just want to tell you one more time that the resonance for the methyl group is being split into a doublet, not because there are two methyl groups on the compound, but because those equivalent methyl protons are being split by the one proton that is adjacent to the methyl groups at the 2 position of the compound.